Good morning, ladies and gentlemen. My name is Zachary Duclos, and this is my partner, Chris Francis, and we will be introducing or reintroducing fiber optic high voltage equipment control system interface. Now, our sponsoring company is Phoenix Electric Corporation, otherwise known as PEC, and they've been producing or manufacturing products for the distribution and transmission industry for over 40 years, with a specialization in custom solutions that are tailored to customers' specific requirements. Now, Phoenix Electric Corporation is one of the few companies that is spearheading trying to protect the grid. So our product motivation entails that, specifically in regards to protecting from electromagnetic interference. Now, electromagnetic interference can come in a variety of different forms, but the main one we're trying to prevent here is the actual attacks, weaponized ones, because the power grid going down in any extended period of time now could be catastrophic. So basically we have a local controller cabinet and a high voltage equipment, and we want to eliminate some of these copper cabling, which are extremely susceptible to electromagnetic interference, and we want to replace them with fiber optic cabling in a cost-effective manner and a safe manner. So the anticipated best outcome of the project was to have two distinct PCB designs, one placed at the local control cabinet and the other placed at the high voltage equipment. This communication system would communicate via fiber optic cable, and we wanted it to be tested and verified in a high quality, in a standard that matched up with PEC's quality standards. This product also had to have seamless integration into the current system, where there wouldn't be any major modifications that had to be made to the local control cabinet or the high voltage equipment. So some of the technical hurdles that we had to overcome in this project and we designed for was controlling the high voltage signals, 125 volts DC with logic level voltage 3.3 volts. The next was these boards had to have over 160 wire-to-board connections that would obviously drive the dimensions of the board as well as the board cost, as connectors are pretty expensive. The board also would have to drive 15 amps on a PCB. As you can see here, this is an example of a PCB that drives high current. So the traces are extremely large, also adding to the board size. I'm going to hand it off to Chris Francis, and he's going to explain a little bit more about our project.
All right, so this is sort of a simplified block diagram of our project. Over here we have our FPGA for the high voltage card, and on the other side is our FPGA for our local control cabinet. Up here we have our two power generation circuits. Now this card right here is what would be placed on the ground in your actual local controlling cabinet. This card on the other side is what would actually go with your high voltage switching equipment. Now in between these two are these four cables here. Those four cables is what would actually be your fiber optic cables. And in between these two cards, you could have a distance anywhere between 20 to 200 meters. So this picture here is a real-life example of what this equipment would look like. Right here is what your local control cabinet would look like. And up over here on the left is where your high voltage switching equipment would be located. So that's where these cards would actually be placed when they were going to be put into use. So, some of our new learning aspects. We had to learn a lot of new skills with this project. First being our design tools. We used dip trace to create our schematics. We also used Xilinx to write our VHDL code. And with this project, we also had to keep in mind a realistic hardware design. And what I mean by that is there are a lot of things we had to think about that you wouldn't normally see in an actual classroom setting. These pieces of equipment are going to be placed outside in the rain, the snow, the cold, the heat, the sun. So I had to keep in those factors, make sure they're able to withstand these temperatures and operating conditions. We also had to keep in an inrush current of 15 amps. That was a big thing that we had to make sure our equipment was able to handle. We also learned about the manufacturing process, what steps it takes to actually create a PCB, and the various things that need to be done to get to the end result. And we also learned about VHDL, how to program an FPGA that would be used in an application such as this. We also learned about different communication protocols. In our project, we ended up going with serverless communication. So our project outcome, we did not quite meet the best outcome we were anticipating in September. A lot of the tasks just took a lot longer than we were expecting. But some of the things that are still remaining is still the design of the local control cabinet PCB. The PCBs would then still have to be fabricated and actually sent to us. And then once we would get those PCBs into us, the VHDL code can be loaded onto them, and we could do an actual real-life testing of them to make sure our equipment is working the way that it should be. So, some of our major accomplishments. The first thing is we simulated our major circuit in programs such as MATLAB and PSpice, made sure all of those were working correctly. Second thing is we generated our schematics for both the local control cabinet and the high voltage switching equipment. We did design the high voltage equipment PCB successfully, so in theory that could go out for manufacturing. And we also designed our VHDL communication protocol, so that is the software that would be loaded onto our FPGAs once we would get those in, and that's what would actually be controlling our equipment. And over here on the right, this is what our PCB would actually look like. That's a snapshot right from our program. So with this project, there's a few people we'd like to acknowledge. First being our technical directors, Sandro Silva and Mike Guerra. We'd also like to give a thank you to our consultant director, Mike Smith. And we'd also like to give a special thank you to our capstone director, Professor Sunak, for giving us this tremendous opportunity.
Thank you.